last time? Where did we leave off? Right, we saw the duality between very simple objects, primitive Dirichlet characters, and automorphic representations, GL1, automorphic fancy sounding things, GL1, Adelic automorphic representations.
That is probably sort of describe what these words mean.
That's right. That's right. So any phi that's an Adelic GL1 automorphic representation is just some constant times the Adelic absolute value to so if it's a unitary representation, then this is going to be something with absolute value 1 times a Hecke character. And this omega is a Hecke character. So it's also a function from the Edel's modulo the rationals to C. It's not 0. And what is it? What's the map? I remind you. So omega of G infinity, G2, and so on, factors into a product of local factors, G, P, GP, with okay, so let's put it here. Omega infinity of G infinity is either 1 or the sign of G infinity. This is if chi, so this is how you get from a Dirichlet character to a GL1 automorphic representation. Last time we went the other way, but of course, I'm claiming there's this duality between them. Exactly. If the character is even, then you just don't do anything. If it's odd, then you put the sign at the infinite place. Let's say the character is mod.
This is kind of weird. You could, if chi -1 is -1, the sign might be 1, right?
The sign could, yes, if G is in the positive reals.
So it's not really like, oh, if it's not really making the match necessarily.
You'll see. You'll see. Yeah. So let's look at the prime powers for a second. And of course, the general chi is just a product of prime power chi's, primitive chi's. And then if L is not equal to, or should I use V? Let's use nu. If nu is not equal to P, so omega nu is unramified, then we set omega nu of G nu. So all we need to know is what values it takes on nu to some power times an element u, where u is in the nu-adic units. And what we said is we would take chi of nu and raise it to the nth power. Okay, so being unramified means it's 1 on the units. And then what does it do everywhere else? Well, you just, whatever the value of chi is at that prime nu, you apply multiplicativity. Okay, and every element of QP cross is some Q nu cross is some power of nu shifted around times the unit. Okay, and if nu is equal to P, then we let so nu P omega P was trivial on.
Saying that nu is equal to P, you're just saying it's ramified?
If we're at the ramified place, yes. So I'm simplifying matters so that we have a single ramified, a single location of ramification. Okay, if nu P is trivial on 1 plus P to the E, I guess, ZP. Right. Then what we do for nu P of P to some power, P to any power, M, times a number of the shape A0 plus A1, P, and so on, plus A e minus 1 p to the e minus 1 plus higher order terms. I don't do anything for the p to the m. And I put here, this is what I said last time. You put chi of a0 plus a1p plus a e minus 1 p to the e minus 1. And don't do anything with anything higher up because that's where omega should be trivial. Okay. This is almost right. We want omega to be a function that's invariant under multiplication by q cross. So we need to check that omega on any non-zero rational is identically 1. Okay. Is that clear? So this, I went through things very quickly with all the technical difficulties last time. So let's actually check this. So let's check it by suffices to check on let's say nu not equal to p. In other words, that omega of nu is equal to 1 and omega of 1 over nu is equal to 1. So I need to know whether this is true. This is a prime. This is a prime different from p. We need to check. Yeah, I need to know that it's 1 on all rational numbers. Rational numbers are made up of primes on top or on bottom that differ from p. The prime p, the ramified prime p itself needs to give us the value 1. So does its inverse. Omega is already multiplicative, already it factors. And there's only one other thing that rational numbers are made up of: primes that are not p on top and bottom, primes that are p on top and bottom. Right. And one more thing to get all the rationals, -1. Yeah. And that omega of -1 is equal to 1. So these are the things that we need to check. And once we check these, we have shown that omega is 1 on q cross. In other words, it's a function on what we wanted, a cross mod.
Sign difference.
Exactly. Okay, so let's look at this. Look at omega -1. So this is a product over all the primes, omega p, including infinity, of -1. Let me call this not p, but nu, because p is our distinguished prime. That the character is mod. Okay, so for nu equals infinity, we have, by definition, omega nu, omega infinity of -1. Well, it depends on whether chi is -1 or if chi is even or odd. If chi is even, then we get a 1. If chi is odd, we get a -1. In other words, we get exactly the same thing as chi of -1 itself. If chi is even, we get a 1. If chi is odd, we get a -1. Because the sign of -1 is -1. Right. Okay. So now I'm trying to prove this. For nu different from p, -1's a unit. So now we apply this formula. We apply this formula with n equal to 0. -1 is a unit. And so we just always get 1. So omega nu of -1 is always 1. That's the unramified case. And finally, for nu equals p, what do we know about this? Well, that is right here. So we need to be able to write, so what's p to the m? M is 0. So there is no p to the m. And then we need to write -1 in its p-adic expansion, which is p minus 1, p minus 1, p minus 1. Yep. Which is the same thing as -1. So this is chi of -1. And when you multiply all of these things together, You get chi of -1 times chi of -1 times a whole bunch of ones, which is 1. So the sign here at infinity is exactly to counterbalance the fact that at the ramified place, the value of -1 is chi of -1.
Have like, an even number of unramified.
Okay, so if you have more than one prime where it's unramified, it's just a product of the different ramifications.
Right, but what I mean is
So-
that here we have exactly one ramified prime.
Yes.
Then, yeah, you'll get chi of -1 squared.
So what I'm saying is if you have a character mod n, so a general character mod n is a product over characters mod p to the e.
Yeah.
Now, if all of the corresponding Hecke characters are multiplicative, then when you multiply over these products, you get the corresponding Hecke character mod for this character. So the Hecke character for a general Dirichlet character is just the product of the Hecke characters for the mod single prime power Hecke character.
I guess that's not where my confusion is.
Okay.
Really. So it's like at the bottom.
All the way at the bottom?
Yeah, like.
Yep.
Right, you're saying that if nu is equal to p.
Yes.
Ramified prime.
Yes.
Then you get chi of -1.
Yes.
But there's also a case where you have more than one ramified prime, right?
That's right.
And so what happens if you have an even number of ramified primes?
So each one of them comes with a chi of -1, chi of -1. Each one of them comes with a pair of these. The chi at infinity will be the product over all of the,
Okay,
so it's not that you get it once, you get it once
Right.
for every,
every
Big-
single time, and so it will match up. Yeah, I was worried you get like a pi minus one odd power.
right,
Oh,
okay? So now we've checked this, we have to check this. So what happens, well, actually, this is the easiest thing to happen, to check. P is a positive number. Okay, so let's check omega of P. Okay, so this is again a product over primes, a product over nu less than or equal to infinity, omega nu of P. Okay. At infinity, omega infinity of P is what? It's either 1 or it's the sign of P, but the sign of P is 1. P is positive. So either way, it's 1. So either way, it's 1.
right, we already took care of the sign case, right? Like,
Right.
it's multiplicative, so now that this upper part has worked out.
Yep. What about omega nu of P if nu is different from P? Well, then P is a unit. It's unramified, so it takes the value 1 on units. For unramified places, P is in Z nu cross. If P and nu are different. So the N here is 0. Does that make sense? Teddy, something you don't like.
How's the n0 against it?
So if we're looking, the thing that we're putting into the argument is P. In other words, not really P, but the, if we want to be technical about it, we're putting in the coercion of P into Q nu. Because that's what this thing takes values on. Okay, P being co-prime to nu is a unit, mod nu. So it's in Z nu cross. So that's what power of nu goes in front of that. There is no power of nu. So it's just N is 0. So this always takes the value 1
That's
for that specific place. And finally, what happens at P? When nu is equal to P, so this is different from this. When nu is equal to P, yep, here's what we do at the ramified place. So it's trivial on this. So we apply the Hecke character to this part, and we shift by multiples of P. So in our case, P is 1, M is 1. We want omega P of P. And all of this is 1. So it's 1 on 1. And then what do we do for omega of P? This is just chi of 1, which is 1. We don't do anything with the shifts of the prime P. Okay, so it's just at the ramified place, they're all just equal to 1. And the same thing with 1 over P. 1 over P is exactly the same. 1 over P is a unit here. It's a positive real number, and its value on WP, omega P is 1.
And the ramified place was but M equals -1, but you were ignoring that anyway.
At the ramified place,
Yeah, that
M equals -1, exactly. But the M makes there's no M on the other side. On the other side of this. Okay.
Yeah, when we look at it like this, it looks really hacked together somehow.
Well, there's one thing we have to check, which is what happens at nu. Okay, so for fixed nu, let's see, for an integer, now let's call this integer L. For L, a prime, different from P, what happens to omega of L? So it's a product over prime, so let's call this L instead of U. L is a prime different from P. We have to check what happens to these things. What's going on here? Yeah. Okay. So again, it's a product over nu, less than infinity, omega nu of L. What happens at infinity? It's 1, regardless of the sign of chi. It's either 1 or the sign, but L is positive. Okay. What happens at nu that are different from L and different from P?
I'm not having trouble distinguishing this computation with the other one.
Okay, the other one was about omega of P, the ramified prime. Now I'm taking an unramified prime.
Oh.
Any rational number is made up of unramified primes on top or bottom, primes, the ramified primes on top or bottom, and -1.
Right, I see. So we took care of it.
We took care of everything but unramified primes. Okay, for L unramified, if I go to a place that's neither L nor P, this L is a unit at that place. And on the units, we take the value 1. Okay. If L is equal to nu, so omega L of L, still unramified, what do we get? On unramified places nu, if you have a unit times the power of nu, you get chi of nu to that power. Nu is L in our application. So if we take omega L of L, we just get chi of L.
Wait, this is
For all unramified places.
right, but L we're taking. Right.
So we're just going to get chi of L. Okay.
And how does chi behave generally again?
Chi is just some character mod P to the E. Chi is a Dirichlet character, mod P to the E.
Right, P being
The ramified prime.
Right. I was just a little worried that if this factored into something including L, then this would just be 0.
L is co-prime to P.
So it's just not appearing in chi.
The primes that are in chi, we trivialized omega at the ramified omega.
Right.
We make act independently of so we just set omega P of P to be 1.
So in a sense, like chi is made out of those ramified.
That's right.
And so saying L is unramified means that evidently it can't be 0.
That's right.
Can't be divisible by around.
Right. Okay, so now what about omega p of L? Let's go to the ramified place and apply L. Here's our last thing that we have to check. And we're going to multiply all these things together. So we go here and we say, what power of P do we need to put in front of L? None. And what do we do with L? Well, we write L in base P, and we just get chi of L. But that's a problem. This looks like we're getting chi of L, which means we're multiplying a whole bunch of ones times chi of L times chi of L. So in fact, what we have to do is put a bar here. And if we do that, then that becomes a bar. And then the product over all places at an unramified prime does come out to 1. And for the same reason, whether it was L or 1 over L, simply reverses whether this is, should I do the last thing? The last thing is the same thing, except if I have 1 over L, I get chi of L to the minus 1. And if I take omega p of 1 over L, I get chi of 1 over L, which is L bar, which is chi of L. So that's the last thing we check.
The rest of it is because the bar is connected to that.
Right. Okay. So just a little correction from last time. I didn't put a bar here. And if you don't put the bar here, it's not a function on the E-del's mod, the rations. To be a function on this quotient, it has to be trivial on that. And now we've checked that indeed it is trivial on that. And everything else goes through. Okay.
This somehow like it seems very special somehow, right? Like it just so works out. Right? These characters, the fact that it's on the circle and 1 over them is just a bar.
Yes.
And all of this is like.
Yeah, that's something that is special to characters. So the real special thing is that any GL1 automorphic representation, being GL1 being abelian, boils down to the character field. One-dimensional representations, irreducible representations, are characters.
The same once we go with not abelian,
then it'll be much more complicated. We'll still have characters, but now we'll have infinite dimensional vector spaces being spanned by the irreducibles will be infinite dimensional vector spaces. Okay. By the way, a little aside. By the way, so aside. You guys had asked, how do you tell if a character is primitive? Right. This gives away. I never thought of this before, and I don't know that it's written anywhere. I'd be happy to be proved wrong. Gives easy method for determining whether chi mod n is primitive. We had discussed primitivity, right? And it's like, well, you have to check all the divisors of chi and see if it's periodic with that modulus. Actually, there's something simpler you can do. Okay, chi mod n. Okay, well, you have to know the prime factorization of n. So, fine. Let's say we know that. Of course, factoring numbers into the primes is.
We didn't know that we would post for the other number as well.
Because you need divisors. Yeah. Okay. Fine. Either way, we need to know the prime factorization. So chi mod n is a product over chi's mod p to the e. Chi j or whatever. These are different characters mod p to the e. Well, they are the character mod n reduced mod p to the e also. But let's look at prime power characters. And the mod n character is primitive if and only if all of these are primitive. Because what does it mean to have a divisor that's okay? I think that's clear. So, and all of these need to be primitive. So how do you tell if a character mod p, how to tell if chi mod p to the e is primitive? Just by looking at its values. Let's go back to what we said. How do we prove this? We said, well, at the ramified places, we are trivial on open sets around 1, with E being the smallest. To be the conductor, E is the least value for which you're trivial on this, on sets of this form, right? For omega P is trivial on 1 plus P to the EZP, with E the smallest, because if I take larger values of E, of course, it's still trivial there, with E minimal. Exactly. So chi mod P to the E is primitive, is imprimitive, if and only if, when you take chi on the values of the next 1 plus A E minus 1, P to the E minus 1, over all possible values of this ranging in FP.
You don't want to make a mistake in that. Right? If you only pick one A, then you might still get 1. But for other values, you may not. You're saying you have to check all of them.
What I'm saying is check the last digit. And if you're always 1, if you're identically 1 as your range over the last digits, then you're imprimitive. If there's a single value here for which, so the contrapositive is, if there exists an A E minus 1 in FP, such that chi of 1 plus A E minus 1 P to the E minus 1 is not equal to 1, then chi is primitive. So that's how you can check primitivity. Is that clear? Does that make sense? Have you seen this characterization of primitivity? I never thought about it this way. It's very simple, but
Yes,
if you're imprimitive, then really chi is a character mod a smaller power, which means on larger powers, it has to trivialize. So as you run over that last digit, if you have a single value that's not 1, you must be a primitive character.
What about maybe this one's going to be so, right? No. It's for each.
It is P steps for each. But it's P steps and not checking over the divisors of N. Well, and then what? And for each divisor of N, seeing if you're periodic with that periodicity. So this is at least slightly better. By the way, you know what? So I looked up what LMFDB does. It does something actually rather clever. Okay, so this is another aside.
it seems like something you find in computational understanding, kind of like textbook.
Maybe. I don't know. I've never seen this characterization of primitivity. That you check the last digit. And if you're 1 on the last digit, then you're imprimitive.
Because normally you just have to check a lot of values.
How do you check periodicity? Right? What I said last time is you take a divisor of N and you see if chi is periodic with that divisor. By the way, when we did let me come back to LMFDB in a second. When we did back to our chi mod 12, back to our 12 table, right? 12 is 4 times 3. So the only characters, so what were there? So Z mod 12, 12, Z cross. All we have is 1, 5, 7, and 11. Right, so these were the values 1, 5, 7, 11, and then we had the characters chi 0, chi 1, chi 2, chi 3. At 1, they're always 1, and then we have our choices. We can make 5 and 7 1, 5 and 7 1 and -1, -1 and 1, or -1 and -1, and then 11 is the product of 5 and 7. I'm just reminding you how we got this table. Right, this was the trivial character. Everybody's 1 on 1, and then you fill out the rest of the character table. And I said, which ones? I said this one's imprimitive, because you can just see that it's a character mod 6. Imprimitive, right? But actually, let's think about that from this viewpoint. So
We need to be primitive for some time.
yes, Yes, some prime power. So what are the characters mod 3? What are the characters mod 3? So the only things are 1s and 2s. And of course I have chi0 mod 3, which just gives me 1. And then I have chi, let's call it chi4, which gives, well, let's call it chi4 mod 3, which is a 1 and a negative 1. Right? And similarly, if I look at characters mod 4, the only thing that's co-prime to 4 is 1 and 3. And then I have the trivial character mod 4, which gives me 2 1s. Or I have the non-trivial character mod 4, I guess I'll call it chi. If I call this chi 4 and this one chi 5, then at least I have a chi 4 of 4, which is a 1 and a minus 1. Now, how can I tell? So whatever these characters are, these are characters mod 12. They have to be products of characters mod 3 and characters mod 4. So this chi0 is obviously the trivial character mod 4 times the trivial character mod 3. There's nothing else it could be. Notice that 5 is 1 mod 4, but yeah, it's all ones. It's going on, it's not a really simple. There we go. Okay. 5, notice, is 1 mod 4, but 2 mod 3. Conversely, 7 is 1 mod 3, but 3 mod 4. So we can read off which character it is mod 4 by looking at 7, and which character it is mod 5 by looking at, which character it is mod 3 by looking at 5. Does that make sense? Am I going too fast? I claim that this character chi1 is the trivial character mod 3 times the non-trivial character mod 4. So this is the trivial character mod 3 times the non-trivial character mod 4. What's this character? It's the trivial character mod 4, because I can read that off from the value of 7. It's the trivial character. So this guy that I said was in primitive, it's true, he is in primitive because he's the trivial character mod 4 times the non-trivial character mod 3.
This is because we're left no choice.
Yeah, if I look at the value, so mod 4, whatever 5 is mod 4, it's not going to contribute to the value of this because mod 4 character is always 1 on numbers that are 1 mod 4. And this number is 1 mod 3. So the character mod 3 isn't going to contribute to this number. So that's why I can read off, it's the trivial character mod 4, but the non-trivial character mod 3. And this guy is the non-trivial character mod 4 times the non-trivial character mod 3. So this is non-trivial character mod 4 times the non-trivial character mod 3. Does that make sense?
So you're saying second and fourth row have to be primitive because they came from products of primitives.
Well, this guy is primitive. I'm saying that when we did our table last time, we went a little too quickly. This one we could see immediately was a character mod 6. This is in primitive. This guy's also in primitive. It's the character mod 3 extended mod 12. And we missed this because we weren't looking at it, or I did it very quickly. Right? It's the character mod 3 extended mod 12. Because mod 3, if we look just at the last digit mod 3, which means look at 1 and 2, I'm always getting 1s here. And here I'm getting, these are both 1 mod 3. Sorry, this is 1 mod 3. Did I say the wrong thing? So this isn't primitive, this is a character mod 6 extended to 12. This character, this character is the character mod 4, extended to mod 12. This is a character mod 4, lifted to mod 12. It's 1 on the numbers that are 1 mod 4, and it's -1 on the numbers that are 3 mod 4. That's its extra periodicity. Does So it's the character mod 4 that has been zeroed out at multiples of 3.
Then like for the third row, you don't have to say mod 6, you can just say mod 3.
This row. Yes, in fact, the character mod 6 is a character mod 3.
So that's the method. You're just looking, in terms of the method that we're talking about before, you just have to look for prime powers, right? So you don't have to look mod 6. You can just look mod
Right,
3.
right. You can look mod 3.
So-
Yes, this is a character mod 3. That's an even better way of thinking that. Okay, so there's only one imprimitive mod 12. I should have known that. So this is the imprimitive. I'm sorry, this is the one primitive character, only unique. This is the unique primitive character mod 12. Okay, so let me show you why we should have known that. How does LMFDB handle characters? So this is LMFDB. They call it the Conrey method. So I fully believe that Brian Conrey came up with this. It's the Conrey method. Method or characterization or enumeration, let's say, enumeration. So here's what you do. So again, you're going to make characters mod chi mod n out of products of prime power characters. And how are you going to get all the characters to prime powers? So chi mod p to the e, the jth character mod p to the e, how many will there be? What will j range in?
You're just saying, this is just some character.
Yes. I want to know how many characters are there and what's the structure of the character group?
This would be like P of P.
Exactly. J in phi of p. Yeah, one to, well, let's say the one way to, that's right. But I could just say z mod p to the e z cross. So I'll just have it literally range in where it naturally belongs. Okay. And how do I determine what its value on an integer n is? Where n is also, so j and n are both elements of, j and n are both elements of the multiplicative group mod p to the e. Okay, so here's what you do. You know that z mod p to the e is has a generator, is a cyclic group. So let g be the numerically least generator mod p to the e.
2, 3.
Probably 2 or 3, not 4, but 5.
Right.
Okay, so you try a couple of those. Once you find, so that like universally determines which g we're going to work with. It's a choice. It's not a canonical choice. Then j is g to some power, let's say a, and n is g to some power b. So the value of this character will be e to the 2 pi I a times b over phi of p to the e. Very clever. So this is a phi of p to the e root of unity. And you can read off whether it's primitive or not. So when is this primitive? Imprimitive if, so the jth one is imprimitive if this isn't a phi to the e root of unity.
Right.
So if a and phi of p to the e have a factor in common. Which is very easy to determine. Okay, so this is a complete list of the characters mod p to the e as j ranges. And it gives you phi of p to the e roots of unity. And you can see that it's multiplicative because if I have n times m, close that door if you don't mind. If we have n times m, then well, let's just check. Chi p to the e, the jth chi of n times m, if m is g to the c, So this is e to the 2 pi I a. Well, the product of n and m is g to the b plus c. B plus c over p to the e.
This seems pretty natural.
It's extremely natural. It's extremely natural. This is how they quantify what all of the characters are.
I mean, when you list out all the characters, you would do. this.
Yes, it's
You would
completely natural. Yes.
Go over the circle and then.
Yeah, but it has all kinds of nice properties. So for example, notice the symmetry between j and n. This is also the nth character evaluated at j. In fact, you could just index this over pairs nj, and there's a complete symmetry. Yeah, you have to do something different for p equals 2. You're absolutely right. You're absolutely right. This is for p not equal to 2. Yeah, and then there's another thing that you do for 2, 4, 8, and after that it sort of stabilizes. Make these choices uniform. Yeah. 2 is always a special prime. Okay.
Yeah.
Okay, so one thing you can do is find what your character is in the database. And then, if it's the jth character and j is, you have to solve the discrete log problem. And then take the GCD of a and p. I don't know if that's harder than checking if the last digits.
I mean, I guess sort of like the point is this is nice for like by hand computations. Really, right? The idea would have been so much.
You mean this or the LMFTE approach? They're not doing by hand. I mean, they're doing massive tables.
They're doing it by computers, but what I mean is that even by hand is nice. Like,
Yes,
if
even
that's
by hand is
things,
for small values. Yep, yeah.
It's like, even if this is an help, like, with 200, 300 digit numbers, like, it still helps, like, conceptually,
That's right.
you're like getting it out by hand.
So you consider representation of the character of the organ, right? Like if you're given the character just as a black box, you can configure it and maybe you give them the geometry is.
That's right. You need time, but not memory. Yeah, you just loop over the values of that last digit. I mean, p could be small. Here's one thing. P could be small, but e could be huge. You still only need p computations to check primitivity.
The power of this person doesn't equal the number of primitive characters. But like, not really, for example,
Yes.
if you better if you have kind of 2 or kind of 4, it can compute how many primitive characters there are.
Yeah.
Based on the price, not from numbers.
Well, chi-mod 2 would give a 1 to 3. So 2 is a bad example, but more generally, no. So if we were doing mod 18 or something, or mod 27, whatever, something where we had larger powers of 3, then it's the last digit. We have to check the last digit, not the first digit. We check 1 plus a e minus 1, p to the e minus 1, as this last digit ranges. That's what determines whether or not, if we get 1s on all of those at the end, then chi is imprimitive. Then we didn't take the largest e, the smallest e for which this is the, we didn't take the largest set around 1 on which omega p trivializes. That's in the largest set like that in the kernel.
So for like a small prime, it's a big power. This not apply.
Yes. Okay. Moving on. What did we do? So this is still review. Also last time, we took a function that was an Adelic Schwartz function. We made a theta function out of it, where t is in the edels, by summing over the rationals except the value at 0, f of qt. And then we took the twisted melon transform, which was an integral over the Edels modulo the rationals, the theta function, times phi. We took our phi of t and multiplied it by a theta series. But phi, recall, is some constant. Let's say that constant is 1 of this quotient times the same theta. And then I have a Hecke character, and then I have the Adelic power. Okay, to something, but I want to have more flexibility here than just having a unitary character. So this is the t to the s Adelicity, d star t. And we opened all of this up, and we got a bunch of stuff times the L function of the corresponding Dirichlet character of S. This did not yet give us the functional equation. So we need the functional equation.
We got something. Right, we want functional equation and analytic.
Yes.
We got one and not the other.
No, we got neither. We just got a realization of this transform as capturing the L function. Because at the unramified places, almost all places are unramified when you do this calculation out. So first we unfolded this into the Adels. By the way, so everything here is trivial on Q. Right? We unfolded and we got f of t, omega of t, Adelic norm, d star t. This factors into a product over primes. This is a local, this factorizes into local integrals, integral over qp cross f p tp, the local character times tp, the p d star tp. And for almost all of these, we got the local factor here, which is 1 minus chi of p over p to the s inverse. And this was only valid when real part of s is greater than 1. All of these equalities so far were only valid when the real part of s is greater than 1. Okay. Now, if you remember, so I want to show you how how similar yet different this approach is when you're doing Dirichlet characters, when you're twisting by characters, to the classical. The classical method, we use the twisted Poisson summation formula. Here we're going to use exactly the classical Adelic Poisson summation formula, untwisted. The Poisson summation formula says that the sum over all the rationals of a function is equal to the sum over all of the rationals of its Adelic Fourier transform. So this is equal to the theta function for the Adelic Fourier transform. We've dilated by t, so we get a 1 over t and a 1 over the Adelic norm of t. We're missing the 0th term, so this is plus f hat of 0 over the Adelic norm of t. And I'm missing from this side the 0th term, which is f of 0. So that's the functional equation. That's the same functional equation we had all along. Okay. You remember this functional equation from the Adelic? This is Adelic. This is Adelic Poisson summation. And now what I want to do is do the same thing to this integral. So again, notice this isn't twisted. There's no chi here.
You're saying it's good enough.
That's exactly, yeah. So the twisting will happen all in the Mellon transform, not at the level of the theta series when you do it Adelically.
Is there any way to do it for pi? Like, is there a way to do the classical thing without doing a twisted Poisson summation?
It's just a different process.
But that's what this process is, right?
That's what this process is. Yeah, because here you're dealing with groups as opposed to just the rings of the integers.
So somehow you can just reduce this down into like the classical regular L-function.
You could, but it would be painful. That's one of the things that's one of the reasons to work adelically. Is that a lot of these computations come out much more naturally and with a lot less pain. The classical version, I think we saw the most general, that it has nothing to do with Dirichlet characters. It's just about periodic functions. Here, we also didn't insist, at least at first, on Dirichlet characters. We just wanted to say, what are the irreducible subrepresentations occurring in the decomposition of L2? And we were led to these Hecke characters. So they're somehow the most natural thing that can be. Okay, so let's take this integral and let's do the same thing we did last time. We'll break the integral. So by the way, this integral, this quotient, we have a nice multiplicative fundamental domain for this action, which is 0 to infinity cross ZP crosses. And now let's break the integral. So the integral over D cross will break into the things that those T's whose Adelic norm is less than 1 plus the integral over D, those T's whose Adelic norm is greater than 1. And remember, this equal sign only applies to the norm is 1 everywhere except at infinity. So it doesn't matter if I put an equal sign here. Here?
Yeah.
Okay. So, well, let's look at the big integral. So what is this? It's an integral over T with absolute value bigger than 1. Remember what this sum over this theta series, this sum over F is secretly a sum over F of n over m times T, with n ranging in the integers.
And what were the,
Well, minus 0.
what were the decay conditions in this?
Okay, so F is a finite linear combination, complex linear combination. So let's just take it to be a singleton of completely multiplicative, factorizable. So F is a product of FPs. At infinity, we have the classical Schwartz decaying faster than any polynomial and all of its derivatives. Mod P, or not mod P, but at the p-adic places, F is locally constant and compactly supported.
Right, and then this is reflected in theta by having, this makes theta have what property?
It makes the sum over the rationals actually be a sum over the integers when we use all of those properties. And so this has rapid decay in T as T goes to infinity.
Very like
At the infinite place, as T goes to infinity in the infinite place, which is all we're integrating over when we restrict here.
right, because the rest of them is like, as he said, this is very finite.
Well, yeah, we have a compact integral. So so the point is, okay, let me just write the theta function, omega, which is a character, so it has size 1, and then we have this T, the Adelic norm to the S D star T. This is an entire function of S. This is entire in S, exactly as before, for the same reason as before, just before we didn't have this extra twist of the Hecke character. When T is less than 1, we're going to do the same thing as before. We're going to stick in, so let me put it, T is less than 1. We have the theta series times omega of T times Adelic T to the S D star T, except theta, I'll now use the functional equation. Theta is this. So this is 1 over absolute value of T, theta F hat of 1 over T. And then the rest of the stuff. So the rest of the stuff is, let me break out these pieces. T less than 1. What was it? It was a plus F hat of 0 over T, omega of T, T to the S, D star T, and then a minus integral over T less than 1, F of 0, no over T, omega of T, T to the S, D star T.
And altogether is analytic.
That's right. That's right. Okay, so I want to work out these two integrals first. Okay.
So review where all of each of the terms come from?
Yes. So all we're doing is we're taking the theta function and applying Adelic Poisson summation.
Those are the three terms.
Those are the three terms. And all I'm doing is I'm taking theta omega t to the s and putting theta omega t to the s, this term omega t to the s, that other term omega t to the s.
And so the one where you use this functional equation it was greater equal.
No, the greater equal is just already entire in s.
Over. Can you say why again?
Yeah, so this is the theta function, which is secretly a sum. This theta function is secretly a sum of f of n over n t, with n ranging in the integers, except for 0. And so as long as t is bounded away from 0, this has rapid decay.
Because of the Schwartz-Mass of the real.
Yes. Okay. So on this side, we're going to get the same thing. I mean, there's a change of variables, and we'll get the same thing with s replaced by 1 minus s. T will go to 1 over t, so omega will be omega bar. And that's that character. What's happening here? So let's work out what these guys are. So for example, let's take this one.
Just to be clear, you're saying that part will be entire. The first term will be.
Yes,
entire.
the first term, yes. This is entire in S, this is also entire in S. It will be in a minute. These were the terms that gave us poles at S equals 1 and negative 1, at 0 and 1 in the case of zeta. Okay. Let's see what this thing looks like. So let's take this one. The other one is similar. So it's an integral over t less than 1. What does it mean that t is less than 1? The norm at all the p-adic places. So this is a product. This is a product over p. Well, let's do the Archimedean one first. So I have an integral from 0 to 1. So this is t infinity in 0 to 1. F hat is a constant. F hat just comes out. And then I have omega infinity t infinity, which is either sine. So it's either 1 or the sine of t infinity. One of those. That's omega infinity. This is omega infinity of t infinity. Then t infinity in absolute value to the s minus 1. And then d dt infinity over t infinity. Because absolute value, yep, times the product. Let's see, I'll need room for this. So times the product over all the finite places of the integral over zp cross. That's what d is. D is zp crosses at all the finite places. They all have absolute value 1. So the condition that t has size less than or equal to 1 is just an Archimedean condition. Everywhere else it's already has absolute value 1. And then what do I have? The p-adic, the local character at TP, the pth norm to the power s minus 1, because there's one down here. I hope someone's checking this, and d star TP.
And this integral is not going to give the prime part is not, as you mentioned, it's like a compact set, everything's below the line, so it's like can't give them.
That's right. This part won't give any issues. It's this part that will give us poles. Yeah, this part we can evaluate. By the way, sine is 1 anyway, because we're on the positives. So this is just 1. And so we're going to get this 1 over s, or 1 over s minus 1. Okay. But let's see what happens here. So some of these primes will be unramified primes, and some of them will be ramified. So if P is ramified, okay, let's do the unramified. If P is unramified, although as you'll see in a second, it'll be a waste to have done the unramified. So the unramified, what do we get here? If it's unramified, then this on ZP is identically 1. then omega p is identically 1 on ZP cross. So we just get the local zeta factor. Local zeta factor. That's all this integral comes out to. If P is ramified, then let's look at the integral. I have an integral over ZP cross. Now ZP cross, let's write ZP cross as ZP cross modulo 1 plus P to the E ZP. Remember this 1 plus P to the E ZP is a subgroup of ZP cross. So I'm just writing a group G as G mod H cross H, 1 plus P to the E ZP. In other words, as I integrate over TP in ZP cross, I can write any TP as, by the way, what is this quotient? Yes. It's Z mod P to the EZ cross. Okay, so I can write it as, let's call it M. This is in Z mod P to the E Z cross times 1 plus P to the E whatever U. Well, it's not U. I'll call it U anyway, but U now is not a unit, it's just an element of ZP. Okay, so the integral over ZP cross, so far so good, does this make sense? The integral over ZP cross is an integral over, is a sum.
Is it like a non-zero?
No, it could be 0. In other words, this is the first P to the E digits, and then these are all the rest of the digits. Could be 0. So it's a sum over M in Z mod P to the E Z cross. And then a sum, well, an integral over ZP. Let me, yeah, okay. Yeah, fine, ZP. And then an integral over ZP. Omega P at this product of two things is omega P at one thing times omega P at the other thing. So I have an omega P at 1 plus P to the EU, and I have an omega P of M. What is the value of T, the P absolute value of TP in ZP cross?
What's a variable where we're integrating?
So we've broken TP, this is U. We've broken TP as M times this thing. As M ranges here and U ranges here.
And the M is not a variable. U is.
Well, M is a variable here, U is a variable there. Okay, D star. Now U, D star M is just a finite sum. D star U is, well, what is D star? D star is D TP over absolute value of TP times some constant. But the absolute value of TP is also still 1. So this is just DTP. So DTP is DUP maybe with times a constant. DU times some constant. Okay. The point is this splits off from this. And what is the value of omega P at M? M is, well, it's the character. This is chi bar of M. Omega P is 1. Omega P is 1 on this set, but it's chi bar on this set. And there's no M dependence here. So it just splits as a product of these two things. And what's the total sum of chi over all possible entries? I'm going to get 0.
And this is what makes the zeta piece.
That's right.
If
If I don't have somebody, if I'm not ramified, if I'm totally unramified everywhere, then all I get is zeta local factors. If I have at least one place where I'm ramified, then this sum will kill the rest of the integral.
So I was wondering this whole time, how are we what makes theta special, right? And then here.
It's that it's totally unramified. It's unramified at every single place. So this integral is going to be 0. This integral by the same token, by exactly the same reasoning, because they only differ by what power it is, what power of t occurs. This integral is also 0.
And again, the fact that there's 0 came specifically
From the orthogonality,
this orthogonality.
this orthogonality. Okay, so now what we have is that on one hand, we have some factors times the L function of chi, which we got only when the real part of S was bigger than 1, from taking this Adelic integral of the theta of our test function at t, omega of t, t to the s, e star t, which we've broken into this integral over d cross with t being bigger than 1, theta f of t, omega of t, t to the s, dt. And we had the other contribution, which is right here. And we make a change of variables, t goes to 1 over t, that flips this, sends instead of t to the s minus 1, we get a t to the 1 minus s. Instead of theta f hat of 1 over t, we get theta f hat of t. And instead of omega of t, we get omega of 1 over t, which is omega bar of t. So saying all of that amounts to writing omega bar of t, t to the 1 minus s. And that's the functional equation. L s chi goes to L chi bar 1 minus s. Okay, so this is entire. This is entire. So as long as you can find something to pre-multiply that never vanishes, like something that makes gamma functions here, gamma functions don't ever vanish, that gives you an entire, because I can divide by that without introducing poles, that gives me the analytic continuation and functional equation. So we get analytic continuation, and functional equation of L s chi.
And what were we multiplying by on the left again?
So what I said, what we did last time is we computed in this unfolding, we computed these local places, and at the unramified places, we got the partial L values, L functions. The ramified places, we got whatever we got, because f could be, f is only the indicator function of z on all but finitely many places. Now, if you make f literally the indicator function of zp at all places, well, w is still going to be something with a character, and you have to see what it adds up to. And in fact, what it adds up to is all of this, because chi at the ramified places will be 0, and that sum will be 1. That's a little calculation we can do. And then at infinity, all you get here is the sine function. So you can take f to be the Gaussian at infinity, and this will come out to gammas, exactly as before.
So you can make this literally come out again.
Yes, in the same way as we did with zeta. The same exact way as we did with zeta.
Yes. So we kept this computation really general, right? And not reducing down, then like, can we still get this like functional equation analytic?
Yes, it's still a functional equation. It's just a functional equation with arbitrary test functions here, and all but finitely many values of the L function being in other words,
These test functions have to satisfy like whatever it is you're.
well, no, the test functions can be arbitrary. It's just that the functional equation you get will be, like if I have some junk here, let's call this junk of S. And now this thing says that junk of S times L of chi S is equal to some other junk. I'm going to replace F by F tilde, by F hat. So I get some other junk at 1 minus S times L of chi bar at 1 minus S.
Right. So in a sense, it's sort of like if your J isn't nice enough, you're gonna lose some symmetry.
It's not that, so if I just divide by J on this side, this is something that we can make sense of. This thing is something that we can make sense of for any value, complex value of S. So if I can make sense of J at any complex value, then the quotient of this side by J is a function that I can put in for any S, which when the real part of S is bigger than 1, agrees with the L function.
Right.
That's exactly what gives us analytic continuation.
I guess what I was saying was more like, you have to worry about what this, like, if you were to physically, like, sit down and do computation with this, you would have to worry about what this Fourier transform looks like.
So if you wanted information like growth rates,
Right, right.
You know,
For
of the-
specific- using a specific depth.
yes,
Right.
then you would want to put choose your test functions to get the corresponding outcomes that you want. Right, so
But it
like a
won't-
Gaussian.
Right, right, but it won't affect this other stuff, so you can actually positively use this J as well.
That's right. That's right. And there are lots of examples where you want to take other kinds of test functions. Maybe we'll get to that at some point. Okay, so in fact, so you saw that these basically boil down to local computations. And let me just set up what we're going to do next time. In fact, what Tate observed that not only do we have a global functional equation, we have local functional equations. The local L functions have their own, also have functional equations. So let me set up a local L function. So L, so definition, come on. Definition, given local character. This is a local character. And given local test function, local Schwartz function, in other words, i.e. Locally constant, compactly supported, we define, let the local L function, L of omega p fp, be the integral over qp, qp cross, I guess, of fp of t, should I write tp, omega p of tp, and the p absolute value to the s p star. Okay, it's exactly what we did above, and it will turn out. This will have. So where is this initially defined? Okay, we'll come back to that in a second. Analytic continuation, and functional equation. And the functional equation is independent of the choice of f. Independent of the choice of f, exactly. Just the fact of the choice. Any other choice of f will give you a different local L value, but the functional equation will have the same quotient. In other words, i.e. For GP, also Schwartz, if I take LP of S omega P FP, and I divide that by LP of 1 minus S omega P bar F hat P, so that's what the functional equation maps S to 1 minus S, omega to omega bar, FP to F hat P. This will be the same, this quotient as a function of S will be the same as if I replace F by G. That's so theorem and the proof we don't have time to do it right now. So we'll do it next time.
So specifically to break this down into a sum, right, into some, like breaking down this interval
Yes.
into sum, it's going to depend on what the specific is.
That's right. That's right, and it gets to have its own values.
So I guess my question is there some like nice choice of app that you can make to give you like series, like?
Well,
we do in
the Gaussian, the local Gaussian is the indicator function of ZP. It's its own Fourier transform. And when you compute this integral, this is exactly where we get the, the classical local L value. So let me just say recall, because we did this. Recall if omega p is unramified and fp is the indicator function of ZP, which by the way is also its Fourier transform, then we did this computation. LFP of this thing is 1 over 1 minus chi of p over e to the s. So the point is, these individually have their own functional equations relating s to 1 minus s. Now,
so that's why it's not only globally, but locally.
yes. So we computed this. Hopefully you remember this computation.
Working on
When with f equal to the Gaussian.
it. Right.
This is the p-adic Gaussian. P-adic Gaussian.
Right, we're sort of saying when you have to get a Gaussian, it allows you to get this Euler model.
Yes,
But if you don't, you let it be something else, then.
it is what it is.
You might not
But
get it.
regardless of what it is, you'll get some crazy integral. You get some crazy function of s here. Regardless of what it is, its functional equation doesn't depend on f.
But we use the Gaussian to get this Euler. And then you just lose the Euler product altogether. You test function.
So when we're doing this adelically, we assume that for almost all values of fp, we have the Gaussian. If you recall. All right.